very good afternoon to all the panelists and attendees who have joined for this online session. The session name is MIPS Instructions, Addressing Modes and Microarchitectures. To deliver the session, we have with us today Mr. Bijoy Varghese, Assistant Professor, Department of Electronics and Communication from Federal Institute of Science and Technology, Angamali. He has completed B.Tech in Electronics and Communication Engineering from Anna University and M.Tech in Communication Systems from University College of Engineering, Anna University. He is currently pursuing PhD in MG University. His areas of specialization include robotics, computer vision, signal processing, and machine learning. A hearty welcome to you, sir. The attendees can make use of the Q&A option for clearing your doubts about this session. Bijoy sir will be answering these questions. So without any further delay, let us start the session, and over to you, sir.
Yeah, thank you, Anita, for introducing me. And I just wanted to congratulate the entire KTU student fraternity, student community, for choosing ASAP as your knowledge partner. And I trust that the PPT which I have shared with all of you is very legible, readable, because the entire class will progress in line with the PPT. That's why. So let us start the session. So the title of this session is MIPS Instructions, Addressing Modes and Microarchitecture. The title itself seems to be pretty lengthy. So I have just shortened the title to MIPS Architecture and Microarchitecture. So the title itself is now very clear. It is MIPS Architecture and Microarchitecture. I didn't do anything wrong with it. And from that itself, one thing is very clear. The 2 points which I have incorporated in the main title, instruction and addressing mode, they comes in the under the title architecture. So before getting to the details of this architecture and microarchitecture, I just wanted to emphasize some important basic or fundamental points regarding a microprocessor or computing. So let us have a look at these points, and after that we will go with architecture and microarchitecture. Yeah. So we are going to start with a microprocessor design. You just assume that you are going to design a microprocessor. So how can we design a microprocessor? What all things we are supposed to do in this microprocessor design? We are going to design a microprocessor because we want the help of that microprocessor. As we all know, microprocessor is an integrated chip. It is an IC. It consists of many circuits. So we need the service of this particular chip. We need the service of this particular circuit. That is why we are designing a chip like that. And which all are the hardwares in this particular chip? The number, the nature, or the variety of this hardware is decided by the services or the features which this particular processor can offer. For example, I am using this particular microprocessor to process something. For example, to process a signal, to process an image, as a word processing. Some other person is using this microprocessor just as a calculator to calculate something. So his service, the service which he expected from that particular chip is to calculate something. And the third person is there. What he expects is, he expects a service like communication. Communication with the external world through internet, by telephone, or by Bluetooth, or any other communication means like that. So that's all about the services. And please do understand that the nature of the hardware depends on the features or the services which a processor is supposed to offer. And now comes to the instruction set. What is an instruction? And my perspective is like, instruction set is something like a toolkit. You assume that you have a toolkit with you. So that toolkit consists of many types of screwdrivers, and many type of spanners, etc., etc. N number of tools are there. That means the power of your toolkit is very high. Like that, instruction set, it is a set. It is just like a bag. That bag consists of many instructions. How many instructions are there? Which all are the instructions? That decide the power or the richness of your instruction set. After all, you need to understand only one thing. An instruction is something which helps us to get the service of the microprocessor. That means microprocessor is capable to give us certain predefined services. The question is all about how can we avail these services from the microprocessor, or how can we communicate something to the microprocessor? The answer is with the help of instruction. So I have defined many instructions which help us to avail or get the service, or which help us to instruct the microprocessor to do something. That is what an instruction and group of instruction forms an instruction set. And now comes to the third point. It is execution paradigms. What is execution paradigms? For example, I will give you a simple example. I am going to use a sequential operation. And as we all know what is sequential operation, there are 5 steps. Step number 2 can be performed only after the completion of step number 1. Step number 3 can start only after the completion of step number 2. That means we are doing something in a sequential manner. The other part, the opposite operation of this is parallel. Nowadays, all are talking about parallelism. Where people are thinking about how to make parallel activities in a computer. Parallelism means what? Or parallel operation means what? There is no need to wait for step number 1 to complete for step number 2 to stop. Hope it is clear. So sequential operation is there. At the same time, parallel operation is also there. Sequential is an example of an execution paradigm. At the same time, parallel operation is another example of execution paradigm. Fine. Technically, there are 3 simple examples. You might heard about the term RISC, R-I-S-C. It is reduced instruction set computer. CISC, it is CISC, that means complex instruction set computer. And you might heard about very large instruction word, VLIW. Right? All these are different paradigms. So when it comes to execution paradigms, you need to understand one point. What it is? Execution paradigm is an arrangement. It is an order. For example, I am going to perform an addition. We know that to perform an addition, we need at least 2 data. So get the first data, step number 1. Get the second data, step number 2. Perform addition between these 2, step number 3. Get the result, step number 4. Store this result in somewhere else, step number 5. So this is an order. This is an arrangement. This order or arrangement will help us to complete the execution, to complete the operation. That is the meaning of execution paradigms. I repeat, step number 1 is to identify the services which we expect from that particular microprocessor, and step number 2 is to design certain instructions which help us to communicate to the microprocessor, which help us to avail the services of the microprocessor, etc. And step number 3 is to define an execution paradigm. And the step number 4, which is very simple, I know the paradigms. I know which all are the instructions that I am planning to use. I know which all are the services we have planned. Based on this, the last step is to design and implement a circuit which is capable to execute my idea. And the last point I have highlighted in red color. That means the last point is completely different from first 3 points. The first 3 points forms the fundamentals of the first part of our title, that is architecture. And the last point, which is logic circuit design to implement the paradigm. That means the hardware part, which is capable to implement what I visualized in step number 1, 2, and 3. And that part is called microarchitecture. Right? So I hope you got the difference between what an architecture is and a microarchitecture is. Fine. So let us go to next slide. Here you can see a simple diagram, and it would be fine if you read it from the bottom side. Fine. So on the bottom side, you can see the last block, which is physics. Okay. So we all have studied about so many physics theories. And in that physics, we studied about the behavior of an electron, which is a fundamental of electronics. By using that behavior, people could create small devices, small components like transistors. That is called an abstraction. By using a theory, we could design something, we could implement something. That is a level of abstraction. And you might heard about LCA, it is lumped circuit abstraction. So the abstraction which we did in the first level, that is physics. And the result of that abstraction is components like transistor, resistor, inductor. All this is called lumped circuit elements, lumped circuit abstraction. By using these devices or components, people could form a circuit which is called an analog circuit. And by using this abstraction over this analog circuit, people could get digital circuits. And I just wanted to emphasize one point here. Many students have a misconception that digital is completely different from analog. There is absolutely no difference between digital and analog. That is a misconception. It is totally wrong. Then what is right? You can get the right answer from this image itself. Digital is the end result of an abstraction which we performed on analog circuit. That is why we studied about TTL, RCL, ECL. We studied about so many families. What is TTL? It is transistor logic. What is the use of this TTL? What is it? It is a family. By using this TTL family, it is possible to form an AND gate. It is possible to imitate the behavior of an OR gate. So NOT gate, for example, is basically made up from where? From TTL. A TTL that comes from analog, that comes from devices, that comes from, and by using these digital components, we can have a digital circuit. For example, we studied about different type of combinational circuit, we studied about sequential circuit, we studied about flip-flop, many things. All these circuits are possible only by using the fundamentals or fundamental elements in digital circuit. The next level of abstraction is very, very important. Next two levels are very, very important because abstraction on the digital layer, digital circuit layer, will give us microarchitecture. That is one part which we mentioned in our title. And the abstraction over that microarchitecture gives us the next level of abstraction, that is architecture. Fine. So what we are going to discuss is, we are going to discuss about this architecture and microarchitecture. And an electronic student is supposed to be very good right from level 1 to level 7. That is up to architecture. You should be very good at physics. You should be very good at your electronics, your digital electronics, microarchitecture and architecture. But a computer science student is supposed to be very good at the top two levels, which are the operating system and application software. If you have fair enough knowledge in the top two levels, that will be added as an extra token for you. Right? So what I am trying to convey from this slide is, We will be discussing about microarchitecture and architecture. These two are just the abstraction over the logic circuits. I have certain paradigms. I have designed certain paradigms. I could note down my requirements. How can I implement it? Just by using the digital circuits. That is what a microarchitecture is. Hope it is clear. We'll go to the next slide. This slide is all about instruction. As we discussed, what an instruction is. Instruction is a tool which helps us to communicate with my master, that is my microprocessor. My processor is capable to do certain things. It is capable to offer certain services. How can I instruct him to do something? How can I request certain services from him? By using an instruction. There are three main types to represent an instruction, or there are three main formats to represent an instruction. Which are the three main formats? The first one is pretty simple, that is high level language. For example, C, C++, Java, all these are high level language. And it is written there in the PPT that it is hardware independent. What do you mean by hardware independent? When we write a C program, no need to think about what is the chipset in my CPU, what is the processor which I am using in this CPU. No need to think about any of this. Instead of that, if we have a C compiler, you can run and execute a C code. So high level language is a human friendly language, a version of English language, and which is hardware independent too. But comes to the next language, that is assembly language. It is just like our mother tongue. The mother tongue of Kerala people is Malayalam. The mother tongue of Tamil people is, from people from Tamil Nadu is Tamil. In Karnataka, it is Kannada. So every people is having its own language. Like that, every microprocessor, for example, Pentium 2, it is a microprocessor developed by Intel. This particular processor is having its own instruction set. Pentium 2, the same manufacturer, Intel. But Pentium 2 is different from Pentium 1 in various aspects. That means this difference will be there in the instruction set. Instruction set is just like the language. So there are some instruction in the instruction set of Pentium 2 which Pentium 1 cannot understand. There are certain instructions in the instruction set of Pentium 1 which Pentium 2 cannot understand. So what I am trying to say is that for every microprocessor, there is a dedicated instruction set. And that itself derives from the services, from the features. So that's all about assembly language. It is a human readable format of instruction. Again, in terms of a form of English language. But it is machine dependent. To write a program in assembly language, you need to know the instruction set of the processor which you are using, you are working with. If you are using a processor of AMD processor, then you are supposed to know the instruction set of that particular AMD processor to write an assembly language. Hope it is clear. Then comes to machine language. It is just a computer readable format of assembly language. That means in terms of ones and zeros, because microprocessor belongs to digital family. It belongs to TTL family. So it can understand things only in terms of ones and zeros. So the binary version of this assembly language is simply machine language. So what is the conclusion of this? You can write a program in high level language, but you need the help of a program which is capable to convert high level language into assembly language. You might have heard about compiler, interpreter, etc., etc. And you need the help of a program which is capable to convert this assembly language into machine language. That is what an assembler does. And the pattern of the instruction is given on there in the bottom side. You can see instruction there. That instruction consists of two parts. The first part is operational code or opcode, and the second part is operational data operand. What is opcode operational code? In very simple words we can say, or we can describe it like, that is a what to do part. What to do part. By using that part, you are saying to the microprocessor that I need the service of these particular circuits. For example, if you need the help of an adder in the ALU, your opcode should be something like add. So that is the real what to do part. To perform this addition, you need at least two data, right? These two data are called operand, operational data. And you can see that in the same slide, you can see that this operand part itself is again divided into two. One is source operand and other one is destination operand. I will give you a simple example. I am going to perform addition between 2 and 3. So 2 and 3 are my real inputs. They are my source operand. And after the addition, I am expecting a result and I am supposed to store that result. Where should I store that result? That part comes in destination operand. So what is source operand? Source operand shows me or shows the ALU from where the input comes from, or from where will we get the data. The destination operand gives us an idea about where I am supposed to store the result. That's it. So please do understand there are two parts. One is opcode part and other one is operand part. Operand we divided again it into source operand and destination operand. Hope it is clear. Now the question is, source operand is capable to show me from where the data comes from. Destination operand is capable to give me an idea about where I am supposed to store this. So which all are the places where I can get my data? Which all are the places where I can store my data? There are many options, but now we are going to discuss about only two. The first one is called memory. Memory means whenever I use the term memory, I meant it is primary memory. That is our RAM. What is the full form of RAM? It is random access memory. And nowadays people are talking about 2 GB, 4 GB, 8 GB in terms of GB. And as we can see inside the computer, RAM is a separate chip. That is a separate chip. That is not inside the microprocessor. That is not inside the ALU. It is a separate chip we can see fixed in that slot. And the second option is a register. And what is a register? A register, again, it is a place to store. Let's just have a discussion about the difference between these two. So what is an operand? Operational data. This operand can be a memory or a register. That means you can store your data in a memory or else you can store it in a register. Right? So let us go in line with this PPT itself. That will be more easier and time saving. The first point is a register is used as a storage element. So what is a register? It is a place where I can store something. That's it. What is a memory? It is another place which I can store something. Right? A storage space. What is point number 2? Number of storage locations are very less. On the other side, it is number of storage locations are more. That means the number of storage locations in a register set is very less in terms of 5, 10 or maximum 20, 30, 50, 60. That's a maximum number. That means the number of registers are very limited. That means the number of storage locations are very limited. For an example, you just consider a building. Building means a building consists of many rooms. So how many rooms are there? There is a number of rooms. And the second point is how much I can store in a room. You just consider your college building itself. In my campus, there are 100 rooms. That means 100 locations. How many students can be accommodated in one room? That is a capacity of a location. Hope you got the difference. So if we consider the register, the number of locations are very less. As I mentioned, it is in terms of 5, 10 or 50 or 60 maximum. But when it comes into memory, RAM, as I mentioned, people are talking about GB. So the third point is access time is very low. So what do you mean by access time? As you studied in your last semester in LCD, logic circuit design, there is something called sequential element, and flip-flop is an example of that. What is the most common application of a flip-flop? A flip-flop can be used as a storage element, right? One flip-flop is capable to store an element, a bit, 1 bit. One flip-flop is capable to store 1 bit. You can use that same flip-flop to manufacture your register. Other variants of flip-flops are there. As you studied, different types of flip-flops are there. And you have already studied about astable multivibrator, right? In your electronics paper. Astable, monostable, bistable. So what is our application of a bistable multivibrator? Can we use a bistable multivibrator as a storage element? Yes, we can use. Hope you know the basic concept of bistable multivibrator. So what I am trying to say is that there are different circuits which is capable to store an element. The question is all about which circuit are you using to store one element. Some circuit can work fast. The performance of some circuit are better than some others. So which circuit are you using? That's all about access time is very low. The technology which you are using to manufacture your register storage location or storage locations in a register is comparatively faster than the technology which you use to manufacture storage locations in your RAM. So to get the data from a register is very, very faster than to get the data from a RAM. That's what we studied about propagation delay and other things in the last semester. And then comes to the next point. It is expensive circuit. Which one is expensive? The best technology, right? So the technology which we used to create a storage location in a register is expensive. The technology which you are using to manufacture a location in RAM is not as expensive as the register location. And the next point is very, very important. Where are these registers? Physically, where are they reside? Registers resides very closer to the ALU inside the microprocessor chip itself. So if you want to see a register storage location, you want to open up the microprocessor chip. That means they are very closer to the ALU. But it comes to the memory, as we discussed, it is a separate unit. It is a separate chip. It is outside the processor unit. Already RAM utilizes slower circuits compared to register. And again, this RAM is in the outside well, I mean not inside the processor. So again, propagation delay will get increased. That means for the ALU, it is very easier to get a data from register than the RAM. So that's all about this PPT. Please do understand. These are the two places where you can store the operand. But these are not the only two places that we will discuss later. Just few points to ponder with this slide. I am going to stop the discussion on the fundamentals of computing. These are just few important points to ponder. As we discussed, there are two places where you can store. One is register, other one is memory. Memory itself are of two types, right? One is RAM, random access memory, and other one is ROM. What is the difference between this RAM and ROM? One is volatile, other one is non-volatile, right? From our perspective, what is the main difference? People are using RAM to store the data. That is what we discuss now. People are using ROM to store the program. Because ROM does not need a supply voltage to retain or to store its content. You just think about the washing machine in your home. There is a ROM inside that washing machine. That is a place where your program gets stored. And that program will be always there. So from our perspective, RAM is mainly used to store the data variables and ROM is mainly used to store the code or the program. That's all. And now, what is RAM? RAM is a memory, just like this building. This is a building. How many rooms are there? Many rooms are there. There is only one memory chip, but it consists of many locations. There is something called register inside the processor. How many registers are there? Obviously, it is not one, more than one. If there is more than one, you need to give a unique address to each and every location. For example, I have a memory. There are 10 locations. That means the size of my memory is 10. There are 10 locations. You need to assign a unique address, a unique combination. For example, if we have 2 bits, how many combinations are possible? 2 power 2 is equal to 4 combinations are possible. If we have 3 bits, 2 power 3, which is equal to 8 combinations are possible. So if you need to address 10 location, 2 power 4, that is 16. Among that 16, you can use any 10 to address the particular location. So each memory or register can be activated by calling its name or its address. What is name? It is just like your name and your class roll number. Whenever I call a name or your name in the class, all of you will receive it, but only you, that particular person, will respond to that. So I have 2 options there. I can call the name of that particular person, or else I can call his roll number. That roll number is address. I hope it is clear. And the last point that is very, very important. Operands or operational data can be stored. If you have 2 data, you can store both of your 2 data in register itself. Or else you can store both of your data in memory itself, in RAM itself. Or else you can store one in register and other one is memory. I am going to store my result. I can store it in any of the register. I can store it in any of the memory location. So these are the 2 options. With this, I am going to stop the discussion on the fundamentals, some basic which we require to go to the next main topic, that is architecture. So let us go to the topic architecture. As we discussed in the very first slide, what an architecture is. It is a programming paradigm. That means an arrangement or an order to complete the execution. Fine. The other name of this architecture, that is programmer's view. It is a programming model. It is the process flow. So how does a programmer view this? How the processor is supposed to arrange the process flow. That flow is called get the first data, get the second data, store it in this particular register, then give the first input to the first input of ALU, give the second input to the second input of the ALU, instruct the ALU to activate the, for example, adder. Fine. Then get the result from this particular pin, store the result in this location. This is what process flow. This is what a programming model is. And the hardware implementation of this architecture, the circuit which is capable to implement what I mentioned now, is called microarchitecture. Hope it is clear. And there are many types of computer architecture. The most popular architectures are x86 architecture, that is developed by Intel. And the next is advanced RISC machine, and it's another architecture. Next is Spark. It is scalable processor architecture developed by Sun Microsystems. The next one is MIPS. That is microprocessor without interlocked pipeline stages. I repeat, microprocessor without interlocked pipeline stages. These are some examples of computer architecture. Among these, we are mostly interested with the last one, that is microprocessor without interlocked pipeline stages. Why? There are 3 main reasons. The first reason is very simple. It is written there in the PPT itself. Many big shots, many big companies, users, this particular architecture, which includes Cisco, Nintendo, Silicon Graphics, etc. Until date, more than 700 million MIPS microprocessors have been sold. That means this much number, millions of MIPS microarchitecture based microprocessors are available in the market. And the last point, which is not included here in the PPT, the reason is MIPS is the main thing which mentioned in the syllabus of KT. So because of these three reasons, we are going to give more emphasis, more importance to MIPS. And the interesting thing is that once we learn an architecture, once we learn MIPS, it is easy for you to understand what x86 is. So what is all about MIPS architecture? Fine. The timer ticks more faster than I expect. So I am also supposed to be a bit more faster. So we completed almost all the basic things. So it will be easier for you to follow. So what is MIPS architecture? MIPS architecture is a 32-bit architecture. That means everything should be mentioned or must be mentioned only in terms of 32 bits. As we discussed, instruction set is there. Instruction is a tool. There is an instruction. That instruction can be mentioned only in the form of 32-bit format. There is an address, memory address. That memory address is supposed to be in the form of 32 bits. I have a data with me. That data must be in terms of 32 bits. I am going to perform an addition between 1 and 2. I just require 2 bits to represent 1 and 2. Even though I require only 2 or less than 32, I must go with 32 bits. If your input is less than 32 bit, you are supposed to make it in the form of 32 bit. That means everything must be in terms of 32 bit. And in MIPS architecture also there is something called register. What is a register? It is a place where we can store something. The title itself says that MIPS register set. It is register set. That means it consists of more than one register. That means you need an address. You need a name to activate it or to invoke it. If you want to store something in a particular register, you need to activate it. How can you activate it? By calling his name or by calling his address. That name and address are given this in the table itself. This is MIPS architecture. We are discussing about MIPS architecture, right? So how many registers are there? 32 registers are there. 32 number of registers are there. That means 32 locations are there. What is the capacity of a location? A location consists of 32 bits. So we have 32 number of register. Each register is capable to store 32 bits. That's it. What is the name of first register? It is 0. What is it is written there in the first column. Yeah. What is the name of the first register? It is 0. What is the name of the second register? It is 80. What is the name of third register? It is V0, V1. Next register is A0. Next register is A1. You can see something in terms of T0, T1 up to T7. You can see something in terms of S0, S1 up to S7. And interestingly, you can see that it is a standard practice to put a symbol just before you mention the name of a register. So when you mention the name of a register, you cannot say simply 0. It must be $0. So 32 registers are there. As per our syllabus, we are mostly interested with 3 types of register. One is the very first register, register 0. The other one is $S. You can see $S0 to $S7. Saved register. The other one is temporary register. You can see $T0 to $T9 or T7. They are temporary register. So we are mostly interested with 3 types of register among these many. One is the $0 register. Other one is the saved register. There are 8 saved register $0 to $7, and there are 8 temporary registers to their $T0 to $T7. And on the right hand side of this name, you can see the address too. What is the address of the register having name $0? It is 0. What is the address of the register $S0, it is 16. You can see it in that slide. What is the address of the register $S1? It is 17. What is the address of $T0? It is, where is $T0? Yeah, it is 8. What is the address of $T1? It is 9. So you can call him hello 9, or you can call him $T0 or $T1. Both you can use. Hope it is clear. So how many registers are there? 32 registers. And what is the capacity of each register? 32 bits. This slide, which I have already explained. Next, we'll have a discussion about the type of instructions. Type of instruction. If you know the services, instruction, and paradigms, execution paradigms, that is what an architecture is. By combining these three, you can form an architecture. So services is always based on the requirement. Based on that, we can form instruction. So what we are going to discuss now is different types of MIPS instruction. There are 3 different types of MIPS instructions. Which are they? The first one is R type, the next one is I type, the next one is J type. The full form of R is register, so register type. The next one is I. I stands for immediate, so immediate type. The next one is J. J stands for GEM, so GEM type. So these are the 3 types of MIPS instruction set. What type of instructions comes under the category R type? As we discussed in one of the first slide, we have an instruction consists of 2 parts, opcode and operand. Opcode is the what to do part, operand is the data part. Operand part is again divided into 2, source operand where I can get my data, destination operand where I can keep my data. If you can get both of your data from a register, and if you are going to store the result also in a register, that means if all the 3 entities involved in this particular operation are registers. I repeat, if you are going to take both of your data from registers and you are going to store the result also in a register among these 32 registers. You have 32 registers, right? You are going to get both the data from any of these. You are going to store again in any of these. That's what called an R-type instruction. So normally, please do understand, if both the source operand and the destination operand are registered, that particular instruction comes under the category R-type. And the next one is I-type. We already had a discussion on which are the 2 places where we can store our data. One is memory, RAM, and other one is register. There is one more memory which is called ROM. What is ROM? Read-only memory. As we discussed, what is the use of ROM? ROM is used to store, as I mentioned, ROM is used to store only the program, mainly used to store only the program, the code. You assume that you have an instruction. That instruction is add. So along with add is the opcode, right? Along with that opcode, I am supposed to add operand. I have kept one in register and I mentioned the name of that register. The second one, I kept it in the instruction itself. I have included it in the instruction itself. For example, add $S0, comma 0 or comma 2. I repeat, add $S0, comma 2. That means my first data is there in $S0. Go and get it. The second data, for the second data, you need not go anywhere else. It is given here itself. It is given in the instruction itself. Where is the instruction? Instruction is there in the ROM. So in essence, we can say that if the data is given in the instruction itself, means data is given in the ROM. So when you take an instruction from the ROM, data also comes with it. Hope it is clear. So if the data is the part of an instruction, you need to give any clue to the processor that no need to go to somewhere else for a data. Instead of that, you will encounter a value now. That value is a data. You need to give some clues to the processor. How can we give that clue? Just by adding a letter I in assembly language. So in assembly language, whenever the processor see or encounter that particular I, whenever you see that particular I, you need to understand that I will encounter a value, and that value is a data. It is not an address, it is a data. That is why it is represented as I type, I for immediate. I just wanted to add one more point to this. This data is also called a constant data. Why it is called a constant data? The reason is, where is the data? It is there in the instruction. As I mentioned, add $S1, 2. 2 is one data. So that data, that particular data is there in the instruction itself, and it is stored there in the ROM. ROM is read-only memory. It is not possible for a user to change or update the content of ROM very simply. So if the data is a part of the instruction, it is not very easy to change that value because instruction is always stored in the ROM. That's all about I type. And comes to J type. It is jump. Fine. Jump means jump to where? Jump to another location. Jump to another memory location. For example, currently the instruction processor is executing an instruction in the memory location 2000. In the next step, it is supposed to go to 2001, but instead of that, I asked him to go to 3000. Right now, I am at Ankamali. Next, I am supposed to go to Alua, but instead of that, the police inspector asked me to go to Trivandrum, jump to Trivandrum, instead of going to the next predefined location. That is what J type. So the police inspector cannot simply ask me to go. If he want to ask me to go, he should add or he should mention the address to go to Trivandrum. So in the J type instruction, along with the opcode, there will be some value. That value will be the address. Where you want to go, you go to this address. So opcode address is J type. Opcode some register is R type. Opcode a register and an immediate value is I type. Let us make, I think it is okay to take 5 more minutes time. Let us have a quick travel to all these 3 slides. The first type is R type. You can see a field pattern there. On the bottom side, you can see the field pattern. Totally, there are 32 bits. The upper 6 bits, that means the 6 MSB bits are reserved to indicate the opcode. That means if you are going to perform addition, add is the opcode. Add is the opcode. So that add must be mentioned there at the MSB within 6 bits limit. Only 6 bits are allotted to you to represent your opcode. Fine. If you are using subtraction, another opcode. Then comes RS. RS is source operand. From where I will get the first data. Then comes RT. It is a temporary register. T is temporary. R is register. So 5 bits are allotted to represent RS. 5 bits are allotted to represent RT. What is RS? Source. What is RT? Second source. What is a source? The place where you may get your data. And what is D? It is destination. What is RD? Destination register. It represents the place where you are supposed to store the result. RS is a register in the register set. How many registers do we have? 32. Each register is having its name and address. How many bits are allotted to you in this pattern to represent an address? 5 bits. What is the reason? 2 power 5 is 32. Right? 2 power 5 bits. 5 is the number of bits. 2 power 5 is 32. How many registers are there? 32 registers. How many addresses do we require? 32. So how many bits? 5 bits. That's it. So 5 bits to represent the address of first source register. Next to 5 bits to represent the address of second source register. Next to 5 bits RD to represent the address of the destination register. Next to 5 bits is shift amount. Suppose if you are going to use left shift or right shift, how many times should I shift? 1 time, 2 time, 3 time, 20 time, 100 time? That should be mentioned in 5-bit format. And the last one is 6 function. Function is again 6 bits. What is the use of function? Hello, please do understand that. In R-type, the upper 6 bits are always 0. Upper 6 bits are always 0. So if the upper 6 bits are 0, what do you interpret from that? It is R-type. If it is R-type, that may be an addition, that may be a subtraction. I'm not very clear about the opcode. The what to do part I'm not very clear. It is mentioned there in function. So please do understand, the lower 6 bits are used to represent the real opcode. Upper 6 bits are used to represent R-type. It is always 0 for R-type. By combining upper 6 bits and lower 6 bits, you can say this is the particular opcode. Hope it is clear. And the next one is I-type. Again, the upper 6 bits are dedicated for opcode. The next 5 bits for one source operand. Next 5-bit RT is not a source operand here. In I-type, it can be considered as a destination operand. The next 16 bits for immediate address. Immediate address. That means the direct address. Sorry, not address, the direct value, the direct data.
So we have 2 questions. Can you please answer now?
Yeah, sure.
First question is C, Python, etc. high-level code or assembly language?
C, Python, all these are examples of high-level languages, and we need a compiler or an interpreter to convert this high-level language into an assembly language, and an assembler, which is another program, is capable to convert this assembly language into machine language.
Okay, thank you, sir. And there is another question. Please explain the importance of the dollar symbol.
Dollar symbol means, yeah, that question is so very sensible. So whenever we represent a number for the processor, it can be considered as a data or it can be considered as an address. So it can be considered from the side of the processor, from the perspective of the processor, a value, a number can be considered as a data or as an address. If you are mentioning a number, if you are mentioning something, and if it is a name, you must put dollar symbol. So whenever the processor encounters this dollar symbol or the corresponding bit pattern, it is an indication that this is the name. This is not an address. This is the name. Likewise, whenever we put I, simple I, in assembly language, it is an indication that the bit pattern which you will encounter now will be an immediate value. That means the data itself. If you simply mention something like some bit pattern, system will consider it as an address. That is what, these are the rules in MIPS architecture. Hope I answered that question.
Okay, sir, thank you so much. And with that question, we come to the end of the session. Thank you so much for spending your valuable time with us, and we look forward to having more online sessions from you. Thank you so much. And I would like to thank all the participants on behalf of ASAP If you want to attend more online sessions, you may please check our website skillparkkerala.in/online classes. Have a good day and stay safe. Thank you.
Yeah, thank you so much.